In a supersized hangar in Paris, an Airbus A380 is being serviced. Technician Charlie Jackson is getting up close and personal with this engineering masterpiece.
As this aircraft is taking off down the runway and generating speed, the tips of the wings actually will raise up, which is a sign that the wing is generating the lift it's going to need to carry such a large aircraft into flight.
Creating a wing big enough to generate lift, but small enough to minimize drag, is an engineering conundrum.
What?
On the A380, special high-lift devices, slats on the front and flaps on the back, allow the wings to increase in size and curve depending on how much lift is needed. But the wings also keep the A380 airborne in a more surprising way.
Inside of these wings is the fuel, which you need to complete your flight.
The plane has 11 fuel tanks, 5 in each wing and 1 in the tail. Fuel is stored in the inner tanks to reduce weight at the wingtips, but after takeoff, it's pumped to tanks across the whole wing. Throughout the flight, the system constantly adjusts the fuel to maintain the center of gravity.
This wing is the product of good design. If it hadn't been that way, it just wouldn't be practical to make an aircraft that size.
Well-designed wings aren't enough to keep this massive plane in the air. Creating engines powerful enough to lift a 369-ton aircraft, along with 200 tons of passengers, fuel, and cargo, almost 2.5 miles into the sky, is a daunting task.
The engines are one of the most important components on this plane. It's like the heart. It doesn't beat, the body doesn't live.
Powering the A380 would be impossible without the brilliant work of past engineers.
History lesson.
By the late 1800s, aerospace engineers recognized that power and thrust were needed to fly. In 1874, Frenchman Félix de Temple attached a steam engine to a monoplane. Et voilà! But the engine was too heavy.
Kablong?
And in 1903, American professor Samuel Langley tried using a giant catapult. But the takeoff didn't quite go as planned.
Yeah, right.
Luckily, 2 siblings from Dayton, Ohio, were about to make one of aviation's most significant breakthroughs.
Hello.
In December 1903, Wilbur and Orville Wright launched the maiden flight of the Wright Flyer. Two propellers driven by a piston engine gave the plane enough thrust to take to the air. Even though the flight only lasted 12 seconds, covering just over 100 feet, it was the first controlled powered flight and is recognized as the birth of modern aviation. But getting a plane more than 1,500 times heavier than the Wright Flyer airborne would take an incredible engineering breakthrough. Through the late 1930s, piston engine propeller planes were the aviation standard. They were limited in range, speed, and altitude. However, a radical engineering innovation was on the horizon. Dr. Ben Evans is experiencing firsthand the power of Britain's first fighter jet, the Gloucester Meteor. It's powered by the first ever jet engine, which was invented by British engineer Frank Whittle.
And a fair acceleration pushing me back into my seat. And these two engines kick into work either side of the aircraft. Maybe that's right? That's good.
Whittle's engines were powerful enough to lift the Gloucester Meteor over 7 miles into the sky at a speed of over 600 miles per hour. As groundbreaking as the jet engine was, the engineering behind it is surprisingly simple.
In essence, the way the jet engine works is you have suck, squeeze, bang, blow. You suck air in at the front here, and then that passes through a spinning compressor. And that compressor squeezes the air down, increases the pressure and the temperature of the air before it passes in to the combustion chamber. And this is the point where the fuel is added and ignited. This increases the temperature and the pressure of the gas even further. And then all of those hot exhaust gases have to expand, speed up through the back of the engine, and they pass through this turbine. And the turbine is connected via a shaft down the center of the engine to the compressor at the front, making that spin. But what pushes the engine forward, what generates the thrust, is the expansion and the acceleration of the exhaust gases out of the nozzle at the back of the engine.
Whittle's jet engine allowed aircraft to fly faster, higher, and farther than ever before, changing the face of aviation forever. To power the Airbus A-380, engineers would need to take Whittle's jet engine design and supersize it.
That size of aircraft couldn't exist before, so they had to develop and to design brand new engines to suit what's required to have it going upstairs in the air.
Upstairs, okay.
While this A380 is being serviced in a giant custom-built hangar, technician Charlie Jackson is getting the chance to examine the jet engines that power this massive plane.
The A-380 has 4 huge engines, 70,000 pounds of thrust each, full of new technologies. It's one of the most advanced engines that's available on the market today.
The A380's 4 specially designed GP7200 turbofan jet engines are among the most powerful ever built. They're nearly 50 times more powerful than Whittle's jet engines, and draw in enough air to inflate a hot air balloon in 3 seconds.
Whatever.
But for the engineering team behind this colossal plane, it wasn't just about power.
The main difficulty is to define an engine that is powerful, that gives economy to the airlines, and reduce noise.
Thanks to its state-of-the-art design, the A380 burns 22% less fuel per seat than the average 747 jumbo.
Oh, innocent.
These fan blades have been designed specially for this aircraft. They have a very revolutionary new shape to increase the airflow through the engine. 70% of the thrust from the engine actually comes from these blades, and not from the motor itself, which is burning the fuel and turning these blades.
The 24 hollow titanium blades are boomerang-shaped with a reverse sweep at the tip. This shape slows the air from supersonic to subsonic speeds, making the A380 more fuel efficient per passenger than a car, and also much quieter.
This aircraft is well below the limits of noise for the size of the aircraft. We're setting the standard.